What happens if a black hole meets another black hole? Do they explode? Do they tear the universe apart? Or do they become something even worse? Because when two black holes finally collide, there is no flash of fire, no giant Hollywood explosion, and no sound in space. But something far more terrifying happens. They begin a death spiral around each other, faster and faster, until space itself starts to shake. And in the final instant, they can release so much energy that for a brief moment, the power carried away in gravitational waves can exceed the light power of all the stars in the observable universe combined. And the craziest part? Humanity has already detected this happening. Welcome to Horizons of Space. Black holes are not empty holes in space. They are incredibly dense objects where gravity is so strong that beyond a boundary called the event horizon, nothing can escape, not even light. That is why black holes are black. Now imagine not one, but two of them, locked together by gravity, orbiting in darkness, each one warping space and time around it. At first, they can circle each other for millions or even billions of years depending on the system. But they are never truly stable forever. Because as they orbit, they lose energy by sending ripples through space-time itself, gravitational waves. And once that happens, their fate is sealed. As the pair loses energy, the black holes drift closer together. Their orbit tightens, their speed increases, the gravitational waves grow stronger. This stage is called the in-spiral. It is the beginning of the end. The closer they get, the faster they move. The faster they move, the more gravitational waves they emit. And the more energy they lose, the faster the whole system collapses inward. It becomes a cosmic death spiral. If you could somehow convert that gravitational wave signal into sound, the pitch would rise and rise in a quick chirp, right before the merger. That rising signal is one of the key fingerprints scientists look for when detecting colliding black holes. And this is where the video gets even more insane. Because black holes do not need to touch like solid objects. Once they get close enough, the very structure of space-time around them becomes violently dynamic. Then comes the merger itself. The two event horizons distort, wrap around each other and finally become one larger event horizon. Two black holes become one. This is not a normal collision. There's no hard surface, no crashing rock, no burst of flame from the black holes themselves. Because black hole mergers are usually dark invisible light unless there's surrounding matter, like hot gas or an accretion disk, that gets disturbed and begins to radiate. In the cleanest case, the main thing escaping the event is not light, but gravitational waves. And during those final moments, the power released in gravitational waves becomes almost impossible to comprehend. In LIGO's first detected black hole merger, scientists estimated that the peak gravitational wave power during the final moments was more than 10 times greater than the combined light power from all the stars in the observable universe. Think about that. For a fraction of a second, two invisible objects colliding in deep space outshone, not in visible light, but in gravitational wave power, the entire star-filled cosmos. But the story does not end at a moment of contact. The newly formed black hole is not instantly calm. It is distorted, shaken, warped by the violence of the merger. So for a brief time, it settles into its final shape by releasing more gravitational waves in a phase called the ring down. You can think of it like a striking bell. The bell vibrates, then slowly settles. A merged black hole does something similar, except the thing that rings is space-time itself. That ring down contains information about the final black hole, its mass, its spin, and whether it behaves the way Einstein's theory of general relativity predicts. So when scientists detect a black hole merger, they are not just witnessing a collision. They are measuring the final trembling shape of a newborn black hole. And now for one of the wildest consequences of all. If the system is asymmetric, For example, if the black holes have different masses or certain spin orientations, the gravitational waves may not be emitted equally in all directions. That means the newly merged black hole can get a recoil kick. In other words, the black hole can be shoved through space by its own gravitational wave emission. NASA has described scenarios where such kicks could even knock a black hole far from the center of its galaxy, or in extreme cases potentially eject it altogether. So the ending is not always just two black holes become one, sometimes it is two black holes become one and then that new black hole gets fired into the cosmos. It's not just a theory. On September 14, 2015, LIGO detected gravitational waves from a real black hole merger known as GW150914. It was the first direct detection of gravitational waves and the first observation of a binary black hole merger. According to LIGO, the signal came from the final fraction of a second of two black holes merging to form a single, more massive spinning black hole. That detection changed astronomy forever. Until then, black hole mergers were predictions of general relativity and simulations on computers. After that moment, they became something humanity could actually measure. We are no longer just looking at the universe, we were listening to it. And since then, LIGO, Virgo and Kagra have gone on to detect many more compact object mergers, including black hole collisions. While European Space Agency's future LISA mission is designed to study gravitational waves from massive black holes in space. Now imagine scaling this up. Not black holes a few dozen times the mass of the Sun, but supermassive black holes weighing millions or billions of solar masses. ESA explains that when supermassive black holes collide during galaxy mergers, they are also expected to release gravitational waves. And unlike many stellar mass mergers, these giant mergers may also involve surrounding gas that can produce radiation as the black holes disturb the environment around them. That means some of the biggest black hole collisions in the universe could be both gravitational wave events and electromagnetic events. Not just invisible violence in space-time, but collisions that may also light up their cosmic surroundings. And that is one reason missions like LISA matter so much. They could help us detect the mergers of massive black holes that ground-based detectors are not built to capture the same way. So what happens when a black hole meets another black hole? First they orbit, then they spiral inward, then they merge, then space-time erupts in gravitational waves, then a newborn black hole rings into stability, and sometimes it gets kicked into space. No fireball, no sound in the vacuum, just one of the most violent events in the universe rewriting space-time itself. And the most mind-blowing part of all, this has already happened many times across the cosmos. And on Earth, we built instruments sensitive enough to catch the universe trembling when it did. If you want more space videos grounded in real science, subscribe to Horizons of Space, because out there, the universe is far more extreme than fiction.